Good afternoon, everybody. Welcome back to another live stream. And sorry, it's been a while. I've just been really busy lately, but I am excited to be back. I was just really excited to see the snow graphics back on my stream. I turn those on this time each year as we come into the end of the year with, the winter season rolling around. And I figure, Thanksgiving's hit. We're not quite in December yet, and I know it's technically not winter, but hey, I'm turning on those graphics. So welcome back to another stream. I'm excited to reboot a project that we started a couple months back. But before we get into that, I do want to talk about give you a quick update on in case you're curious about some of the other projects that we've been working on. So we have been working on 2 other projects, and in case you are wondering what the status on those are, so the first one being the computer vision rock paper scissors project. That one definitely still is ongoing. So transparently, just the reason I've not done streams lately is just I've been busy in general. So like that's the number one reason why I've not made much progress on some of these projects. But with the CV rock paper scissors project in particular, I have run into this roadblock of trying to get TensorFlow installed on my MacBook. So I have one of these newer Apple Silicon based MacBooks running with the M1 chip. I just cannot get TensorFlow working right on it. So I've been trying not to use Anaconda, and in case you're wondering why, and the reason is I try to do everything that I try to do on these streams is I want to make it as cost effective as possible. And so even though Anaconda is free for limited users, if you do want to use it in an enterprise fashion now, they do charge for that. So, and nothing against Anaconda, of course, but if we can do it without Anaconda, I would prefer not to. But I think I'm gonna have to cave on this piece. So more to come on the rock paper scissors project, and then the other project. So it was just a reminder. It was going to be a natural language processing project that looked at the sentiment analysis of tweets to analyze the potential impact on how stocks are influenced. So I called it the ticker tweets project. To be completely transparent, I don't know if I'm going to continue forward with that project. And it actually has nothing to do with Twitter. You might be wondering, does it have anything to do with the recent Elon Musk acquisition? Actually, no. There are 2 main reasons why I'm considering not moving forward with that project. Number one is whenever you may have seen this in the actual stream because I did one stream on this already looking at the Twitter API. The data that I was getting back that we're using, because we're using the hashtag symbol, which is basically like a hashtag but with a $ symbol. The tweets that we were looking at were just basically garbage. There was nothing, there was nothing substantive, and at least as of today, the Twitter API has not been updated to do more robust searches. So I may wait until then. But actually, the more important reason is I actually tend to take these blog posts and I write them I take these live streams and write them into blog post form, and then I submit them to the publication toward Data Science for better reach. And when I submitted this first one toward them, they and this is again nothing against them. They're very kind folks. They basically said, we're not really interested in posting anything about stock market analysis. So they declined my blog there. So given the weirdness of the tweets that we were receiving, and I guess there is some uncertainty of what's going to happen with the Twitter API in general. We may not proceed forward with that project. So if anything, I do want to get another project. So I don't know if you noticed my strategy so far with all these live streams is I'm trying to get projects that cover a wide breadth of different topics. So we've already covered, a structured data effort. And in this one, we're going to be covering, some basic computer vision. And then the rock, paper, scissors is some more complex computer vision. Excuse me. And so I do want, a natural language processing sentiment analysis. I want a topic modeling one. Transparently, the hardest part with coming up with these streams is not figuring out the tech behind it, is just the creativity to come up with an original project. And so actually, and I guess that brings us back around to our project today. So I can't believe it's actually been well over a full year now since I've actually initiated this project. And this actual project was not incepted for me. So just to give you a bit of a recap, on what this project was is, so I have been a mentor at the local high school through my company State Farm to help them. So basically, they go through this 4-year program where at the end of this program, if they complete it successfully, they will graduate with both their high school diploma and an associate's degree in computer science. And as part of the capstone of this program is they were basically given free reign to determine a project that was basically like any sort of computer-based project. And so they determined they wanted to create this project that was, okay, we want to use computer vision to analyze how long it takes people to get out of the school parking lot. Because I guess, at the end of the day, there's a lot of congestion when it comes to getting out of the school parking lot. So they wanted to see how that timed out. And so that was well over a full year ago now. And so actually, as of today, they will present on their final presentation a week from now. And so things have changed a lot between now and then. So I offered to mentor them specifically because I wanted to learn alongside them, essentially. Because I'm a little bit greener in terms of computer vision. And so when I helped them scope out the project, and this is all on me, I think I let them get a little bit wide with their scope, so that we did end up paring their scope back quite a bit. And so what they ended up doing is essentially what we're going to end up doing, except they took a different fashion to it. And actually, kudos to them. They ran with this, with a particular piece of this without me. So what they ended up doing is they ended up creating this detector that basically looked at a parking lot using yellow V5. So I did help them figure out the yellow V5 piece. And then, but whenever they basically took whatever they detected in the actual video and then converted that into a drawing on top of an image. And so they actually used, I think, Detector for that. And so that Detector drawing piece, so the conversion of, the bounding boxes that were on the actual video to this drawing piece with Detector, they figured that out all by themselves. So I'm actually extremely proud of them at the end of the day. So that's actually what we're going to be doing with this project, except we're going to be doing things differently. We aren't going to be using Detector. I think that was a fine approach that they did. I think there is a better approach, and the only reason I've actually now come up with a better approach is I'm now taking this computer vision course on Udemy, and so I guess I should throw out a plug for that. So Jose Portilla has this course called Computer Vision, and so I basically am applying a lot of the concepts that I've learned in that course so far to what we are going to be doing here in this live stream today, and then in the subsequent live streams going forward. Okay, so basically, let me go ahead and share my screen here. All right, so what we're going to be covering here is, imagine that, so this is, by the way, is Affinity Designer. Affinity Designer 2, actually, just came out recently. I'm pretty excited about that. So imagine we have this drawing of a parking lot here. What I want to be able to do is use a computer vision to basically know, okay, when a car pulls into a parking spot right here, let me go ahead and draw, a little rectangle, and we'll make it red representing this car. Let's say this is a car. Then I want the computer to say, okay, this spot is filled. And at the end of the day, I want to be able to basically count the number of spots and see how many are still available. Now, I don't actually, so I created this basic drawing using some basic rectangles in Affinity Designer here, but I actually don't want to use Affinity Designer for the basis of what we will be drawing at the end of the day. I actually wanted to use computer vision from scratch. I actually want to look at the parking lot with a webcam and have it by itself determine where the lines are and draw the lines and determine where the parking spots are at for everything. And I think there actually is a way to do it. So I'm pretty excited about that. Now, we aren't going to get that far today. But I did just want to kind of give an intuition of where we're going with this basic drawing right here. So with that, I do also want to show, I created a little bit of a demo station over here. So off on my right over here, and this is harder to see. So I created this fake parking lot. Here, let me go back to just me for a second. So this is my fake parking lot. This is nothing but, basically cardstock paper that I got from Hobby Lobby. And I got this really thin, where is it at? I don't have it with me right here, but this is basically duct tape, but it's really thin. You can buy it on Amazon. So, and then off to the right here, as I was showing, is I have this little arm with a USB webcam connected to it that's pointing straight down. So I think this is one of those arms that I think like tech YouTubers use for like reviewing, new devices or whatever. So when I slide this back over here, Hold on just a second, folks. All right, so let me go back to my demo station over here. So now I'm going to slide this back over onto here. Okay, and so this is basically what I'm going to be using for my testing purposes. And so again, like I said, we're actually not going to be doing any sort of actual vehicle detection today. So just to get that out of the way. So if that's what you came for, I apologize. We're not going to be doing that today. We're just going to be doing some basic image processing today. But I want to give, set the table on where we are going with this project. So, originally, again, like I said, the high schoolers that I was working with, we wanted to analyze how long it was going to take to get out of a parking lot. I still think that's possible. I think there's just some challenges and some scope creep associated with that. And so to make things a little bit more simpler, and this is still going to be a really cool project. Basically, so what I want to do here, so I got some toy cars here. So this is, here, let me go back to just sharing me again for a second. So these are Hot Wheels cars. This is actually a Tesla Model 3, a white one and a blue one. And the reason I have two is, I've shared this story before. 5 years ago, I really wanted a Tesla Model 3, and my wife said she would get me one for my birthday, and so she did. She got me this white one as a joke. And then eventually, about 2 years ago, I finally did save enough money to get my own Tesla Model 3, and that is my blue one. So I do have a blue car, but it's nice to have the white car because, as you can see when I pull up my demo station here, it's actually a lot easier to view with my stuff here. Now my lighting is kind of funkily set up here right now because I got the mood lighting, if you will. So when we actually start to do some of the computer vision stuff, I am going to turn on all the lights in my room and turn them all white. That way we have a very clear white parking lot. But this is just giving you a preview of where we're going to go. So basically I want to start up this program, and it's going to draw the parking lot lines and detect where the spaces are at automatically for us not doing any sort of drawing or anything. And then whenever we have a car parked in a spot like this, so, or even, one over here as well, or I guess one over here, then, or if stay, then it'll say, okay, those two spots are filled. And so this is my little demo station. I think it's, it's pretty rudimentary, but these are, I tried to make these, or get some realistic looking cars. I do have some other cars back here that are not as realistic looking. So this is my Super Mario World VW bus. I don't know if this will be detected, but we are going to be using a pre-trained model, but it's actually not really a model, and I don't really want to talk about that as much today because I've learned some interesting things about computer vision in the last couple weeks. Excuse me. So so let us go ahead and move on into actually doing some live coding because that's what y'all came here to see today. So I actually went ahead and took a still shot image of just this empty parking lot, and I did turn on all the lights. So if you would like to follow along, this actually is up in GitHub's today. So let me go on over to show you my GitHub. So if you go up to my GitHub, and just to be completely transparent, I went ahead and, I've tried to do real live coding before where I tried to figure out things on the fly. For those of you who have been around long enough, you've seen me flop with those. So I do have to pre-prep beforehand. So basically everything that we're doing today is covered in a robust Jupyter notebook here. But if you come into the root level of this repo here and you go into data, you will see the same raw image of that we will be working with. So let's go ahead and jump into an empty notebook here. Okay, so like I said, I already did capture. Here, I'm going to go ahead and show this. Oops, no, that's not what I wanted to show. Okay, yeah. So this is basically like I have my demo station up on the top right, me on the top bottom right, and then yeah. So in case you want to, do I want to keep that up? No, I think I'm going to take that away. All right. So I basically took a screenshot of that, and then we're going to read that in, and we're going to be doing some image processing on that. So the primary library that we're going to be interacting with today is a library called OpenCV. So CV obviously standing for computer vision. It is imported as CV2, and I can't remember the precise reason that is. I believe there was a Python version called CV1 before, and so naturally, whenever enough stuff changed, they incremented that to computer vision 2. This is a Python, this is a library that was originally created by IBM, I believe, in the early 2000s, and it was originally written in C, and I believe it still largely has its foundations on C. And so we are going to be using the Python wrapper for it. So the way that we import that is just, so I think the pip install is like pip install OpenCV Python. Here, let's look really quick. Py. So pip install or OpenCV. So this is the one interesting thing about that I've never really understood about PyPy is like it's not really ordered like which one is the most popular one, because I know it's none of these. Okay, well I'm pretty sure it's like open or like pip install Python CV or something like that. Anyway, so that's the primary library that we're going to be interacting with is CV2. So, and that is actually how I captured this the picture of my parking lot over here. Here, let's get this thing out of the way. And it's how we're going to be interacting with the images. It's going to be how we interact with the video. We start up the video and all these things. And by the way, I should mention I am monitoring for questions on both LinkedIn and YouTube. So if you have any questions, feel free to drop them in, and I'll answer them along the way. So CV2 is the primary library we're going to be working with. And then the secondary library that we're going to be working with, particularly for visualizations purposes, is matplotlib. So matplotlib, here, let me make this a little bit bigger for y'all. Matplotlib.pyplot, import matplotlib.pyplot as PLT. So that's a common what's the word, alias that people use for matplotlib. And so this is basically the general purpose Python library that people use for visualization of, data visualization. So if you actually, my previous live stream was all about data visualizations with Halloween Candy data set. You might recall that we use Seaborn and matplotlib quite extensively. So we're not going to be using matplotlib that extensively here, but we are going to be using it to show our images appropriately. Now, I am going to add the magic command here as well. This is actually uncertain if this is required anymore. I think I read in newer versions of Jupyter that you actually don't need this anymore. But basically what this magic command here is doing is saying, okay, if I'm using matplotlib, I want to render my visualizations within the notebook here. So you may or may not need this. I'm going to put it in just to be safe. So that is let's go ahead and import these. So matplotlib, sorry. All right. Now, so how do we import an image? So importing an image is as simple as using CV2 a function called .imread. I'm assuming that im stands for image, so imread, and we're going to go to our file path. So our file path again, so I am in the notebooks directory of my Git repo, so I got to go up one, and then I got to go into data, raw, and then my empty parking lot. Now, CV2 is a little bit interesting in the sense that it reads in color channels a little bit oddly. So what I mean by that here, let me go ahead and show you the shape of what this image is. So you could see that, the shape of the image is, it's a 1080 image, because this is a 1080 webcam, 1080 by 1920. And then you might be wondering, well, what does that 3 represent? And the 3 represents 3 color channels. And so I've talked about this before in previous live streams, but just to reiterate, looking at whatever screen you're looking at. So whether it be the screen that you're watching this stream on right now, or your iPhone screen, or, even a watch like my Apple Watch here. These are all comprised of pixel values. And so every single one of the pixel, the way the computer knows how to render the color of the pixel is by basically lighting up these 3 different color channels associated to each pixel. And every single pixel has these 3 different color channels. So it's typically red, green, and blue. So, and then to go even more granular, the colors, the numerical ranges of these color channels usually span from 1 to 256. Now, obviously, because we index things at 0 in Python, it usually goes from 0 to 255. Just keep that in mind. It's 1 to 256. So, but the kind of the interesting thing about CV2 is that it actually does not default to an RGB color format. So, like I just said, most computers read in things as RGB, red, green, blue color channels. It actually reads things in as blue, green, red. So if that doesn't make any sense, let me go ahead and show you. So the way that we actually show the images is we're going to use matplotlib. So we're going to use mshow. I'm going to pass in the image. And then let's go ahead and show it. So obviously this does not look right. So these lines are very, very blue. And you can see here, pulling back my parking lot, that's not blue. So, and the reason this is, again, is because it is reading these color channels in a different way than we were expected. So the thing that we have to do first is we need to convert this image from a BGR format to an RGB format. So that's one of the first things that we're going to do here. So I'm going to, fortunately, this is actually very easy to do with CV2. So the way that we do that is cv2.cvt color. So that stands for, I think, convert color. And then so we pass in the image, and then we pass in a secondary value that is going to be cv.color. And then so when I start to, cv2.color. All right, so when I start to do the tab autocomplete here, you can see there's a lot of different options that we can select from. So what I want to do is the underscore BGR to, and then we can change it to a number of different values. And so I actually am going to show how like one of these other ones for now, but I do want to just do the one that I want to do for now. So BGR to RGB. Where is BGR to RGB? BGR to RGB. There we go. All right, so now the image has been converted to the correct color channel. So if we were to display this image again now, as such, you can see now that looks about right. Okay, so that is the same parking lot that we are working with here. It's just a static image. This is not live, and obviously you can see it's not live because I'm holding it right here. Okay. So that is just simply reading in an image. Now, oftentimes we may want to, not interact with a color-based image. We would prefer to work with a grayscale image. And now the way to convert this image to grayscale is very, very similar. It is the same basically as how we converted from BGR to RGB. It's just a little bit different. So I'm going to say gray image equals cv2.cvt color. I'm going to pass in the image and then CV2, and then so it's going to be color. Now, if you recall, you could probably figure this out for yourself. This is RGB, so we're going to start it off with RGB, and then we're going to, and you could probably figure this out from here. We're going to go to gray. So I'm going to run this. Now, here's where things get interesting again with Matplotlib. So by default, whenever Matplotlib displays a grayscale image, it actually uses a color mapping known as Viridis. I think I'm pronouncing that right. So let me find a link. So Matplotlib Viridis. Viridis. Okay. So these are different color maps and stuff. So basically, and the reason that it selects Viridis is I believe that this is more representative of what the human eye sees. I'm not perfect of understanding these sorts of color things. This is just more, to help you understand why you might be seeing some goofiness whenever you start to load up these images. So basically, by default, whenever we load up or we display this color mapping or the grayscale image, it's going to show it in this Viridis color format. So this is ranging from like a yellow all the way to like a teal in the middle to like a violet. And so let me show you what I mean here back in our notebook. So when I go and display this image, so displaying the image is plt.imshow gray. Okay, so obviously this is not what we were expecting. Again, so this might freak you out. So you might be wondering, well, what did I do wrong this time? You didn't do anything wrong. This is just by default. Matplotlib decides to display grayscale images in this Viridis format. So if you want to update this, it's as simple as updating the imshow. So we're going to pass in the gray image again, and we just need to change the color mapping. So comma cmap equals gray. Okay, so now that is the correct color mapping. So that is the basics of how you're reading an image and changing the color formats. Now we will be changing the color formats once again for another thing later on, but that's just some basic of how you get these things in order to be able to process them appropriately. Now, the next thing I want to show you is something called image thresholding. So let me just go ahead and show you first, like what actually is inside this image. So basically, these images are arrays of values. So so you could actually interact with these with NumPy. You'll notice I did not import NumPy here, and that's because I don't necessarily intend to use it today. So these are all just integer values, and these are all just representing the pixels that are associated to each of the rows and stuff. So I know this is a little bit difficult to read, but again, these are the 3 color channels here. So 46, 46. So that would be RG. So that would be like a little bit like halfway between red and green, and then a little bit more blue. and then so on and so forth. And so the reason I wanted to pull these up is so you can actually take these numbers, and if you wanted to, you could threshold them in such a way to where like only like certain ones like are shown. And so it's actually easier to represent with the gray image. So let's go ahead and look at the gray image really quick. So the gray image here, we instead of showing the 3 color channels now, we are just showing the 1 color channel of grayscale. So we have now flattened the image instead of having the 3 color channels to have the 1 grayscale image, so it's only represented by a single number. And so what we're going to do with thresholding here is basically saying, okay, you know, we have these color ranges between here. So I just want to show like what is the max that is being displayed here. So the max, I believe, I think 0 is white, and then 255 is gray or black. I might have that backwards, but basically, it's what thresholding is saying is, okay, if I have that's what I was going to show. So the max value here is 174, so it actually does not go all the way up to 256. Interestingly enough, but like let's say I only want basically anything that is so I see like 95 right here. If it let's put this at as our thresholded value. If it is anything below 95, knock it to 0. Anything above 95, make it pure black. And you might be wondering, well, why do we want to do that? And so, and what it is going to show us is it's going to really create a contrast between like whenever we set the threshold value, then everything above that is going to turn black, and then everything below that is going to turn white. And so the way that we do that here is using a function provided by CV2 called CV2 threshold. So by the way, so I really do like CV2, but I've mentioned this, or OpenCV, I guess, but I've mentioned this before, 2 things. Number one, their documentation is challenging, and that is the nicest way I can put it. So if you, like, let's go ahead and look at the, I'll go ahead and show you OpenCV mread. So this is the same function that we looked at before. Like this is just this is very difficult to read and understand like what it's looking for. So like even if I like hone in on here, I'm not really sure exactly what it's asking for or what it's saying. My only advice is if you really want to know something. So I did a Google search here. Scroll down a little bit and look for Geeks for Geeks, because Geeks for Geeks usually has a better like description of what this thing is doing. So what they're saying here is, okay, so mread, you can pass in like a string to where this is being read, and then a flag of like how it should be read. And so we didn't pass in any flag, but actually, you know, if we went back into our notebook here, and if I were to put in a 0 right here, this actually would read in as a grayscale image by default. Okay, so just note that. So why did I say that? I don't remember why I said that. Yeah, I don't remember why I brought that up. I had a point for bringing that up, but I don't remember now. So, yeah, that was one of my secondary point. Now looking at this, some of the return values are kind of weird for some of these functions. So with the CV2 threshold function, it actually returns 2 values. It returns the cutoff value and the actual image itself. And you might be wondering, well, why do we need to know the cutoff value if we're passing in what the threshold cutoff is? And that's my point. So what I'm going to put in here, so I'm going to put cutoff, comma, thresh image. So this is going to be what's going to be returned back to us. And I might need to move my head out of the way. Here, let me move my head out of the way for you. All right, cutoff thresholded image equals cv2.threshold, and then we're going to pass in the gray image. Okay, so now we're going to pass in this parameter, and this parameter is going to be what we want to set our threshold to be. So let's say our threshold here is 125. So basically any of these values that we see here in the gray image, so anything that's below 125, so this 49 will get knocked to 0. Anything above 125, and we actually don't see any examples in here, but there are examples, I assure you, will get elevated to the max value. So, and that's the thing that we're going to set here. So the max value here that we're going to set is 255. Now, in order to, we can actually set a type of thresholding that we want to do with this type flag here. And so what I want to set here is a thresh binary. So we can actually, here, let me go ahead and start to, or CV, I always forget that, cv2.thresh. And so let me go ahead and do like a tab autocomplete. Oops, So you can see there's actually a number of different tab things that you can do. And if you want to go and see Google like what each of these does. In fact, I might show the binary and the binary inverse. It kind of makes sense like what each of those does. Or I'll show all three. So let me go ahead and just select threshold binary for now. Now, so run that. Now here, this is what I was mentioning is I don't know why this cutoff value is returned. So like let's go ahead and print the cutoff. Print cutoff. Okay, it's 125. That's the same thing that we pass in. Why are we returning a value? Like, okay, so this might be my naivete speaking. I just don't understand why we are returning a value of a parameter that we're passing in. Like that, it just maybe there is an instance of which you would want this, but in my opinion, I don't know. This just doesn't seem to make much sense. But you do have to have both of these values here because if I were to just say thresh image, here, let me just go ahead and do this. Thresh image, then and then look at plt.imshow my thresh image. It's gonna like get mad at me because it's not gonna know what this is. And if we then look at this, it's the cutoff value. See, it's got both of them in here. We just a little bit of tuple unpacking there by adding this cutoff in here. So be sure to include that, even though I personally think it's a little bit goofy. But yeah, so let's go ahead and actually show the thresholded image now. So let me cut out this cell. Cut this cell out. All right, so PLT show that thresholded image. Oh, forgot about my color mapping. CMap equals gray. Okay, so what it's basically showing here is, okay, so it's really interesting what this is kind of displaying here. And it probably doesn't make any sense to you, but it makes perfect sense to me. So you can kind of tell here. Here, let me go ahead and go back to just me for now. Okay, so off of my setup, so this is again where I took the image from right here. You can see the lamp back in the corner right there. So you can see there's one light source here. What you can't see, what I'm touching right now with my other hand, which is on, so this is the other side of the parking lot essentially, is a ring light. And so if I come back to, let's go ahead and look at this again. What that's basically showing is the two different light sources. So it is very difficult to see off this piece of paper up here just by default, but by doing this threshold here, we can actually very clearly see, oh wow, there's the two different light sources here. And so it's pretty cool to be able to do things like this. Now, honestly, we're not going to have much utility for something like this, but I do want to show you these are the different kinds of things that you can do with OpenCV to demonstrate, like, okay, like these are the different kinds of things that, you know, maybe I should consider when I start a new project. All right, so and again, I mentioned before that we could change the type of this to inverse. So inverse obviously is kind of what you expect here. And then what were some of these other ones? I can't remember what Atsu does. I can't remember what Atsu does, but let me thresh. I know one of these does. I think the 2 zeros. I think like one of them is if it's below the value, then it knocks them all down to 0. And if it's above it, then it just keeps it what it was. Yeah, I think that might be what it is. So you'll notice that the parking lot lines here, or maybe, yeah, because this is the grayscale color mapping. I can't remember. If you do want to look at what those are, it's like actually so sometimes the documentation is kind of good for OpenCV. So OpenCV threshold. So if you look at the image thresholding here, you can actually see examples of like what it's doing here. So the binary here is obviously just doing a straight binary, and then you can see the 2 zeros, and then so sometimes the documentation, it can be good. I just find it like in practice. So so here I can talk of like what is the dichotomy of when it's good and when it's not good. It's good when you want to talk about a concept. It's not as good when you're trying to actually practically apply something in the form of code. So like. Yeah, when we're talking about the concept here, like the documentation is actually pretty good. Okay, so coming back to here, so that's some very basic thresholding. Now that's just doing a simple thresholding based off of that set value here, and we could fiddle around with this value. So let's turn this back to binary. Like let's say I turn it down to 100. So now you can see that we're not getting much now, but if I turn it up to 110. Now we are getting a little bit more, but not much. So that's why I selected 125 from beforehand, because I tested out a couple of numbers before. And now we're seeing a little bit more of the parking lot. So Yeah. So if you're not a fan of this like pure binary thresholding, there is another kind of thresholding called adaptive thresholding, and you may have even seen it here on the page. And it's basically using some math under the hood to determine little bit better of an adaptive threshold here. So it's relatively simple to apply. So the way that we're going to do that, we're going to call this adaptive thresh image. So adaptive threshold image equals CV2 dot adaptive threshold. So we're going to pass in our gray image again, and we're going to do a max value. Max value equals 255. Okay, adaptive threshold, adaptive method equals CV2 dot adaptive thresh mean. See, so in case you're wondering what this is I believe what this is doing is it's passing some sort of kernel all over the image that is basically looking for like, okay, what does the neighboring pixels kind of look like, and trying to gather a thing there. And again, the documentation here kind of explains this better. Okay, yeah, it even says right here. So the threshold value is the mean of the neighborhood area minus the constant C. So we do have to set the constant value here. So, and you'll see that here in a second. So threshold type equals cv2 dot thresh. We're going to just do a simple thresh binary again, thresh binary. And then block size. What is block size? I think block size is like how big the neighboring area should be. And it has to be an odd value because because of the kernel size it can't be an even value. I thought that was in here. Okay, well, I may be going, or might be misremembering that. All right, so 11, and then I'm going to set a constant value to C equals 5. Okay, so now let's go ahead and look at that image. So plt.imshow, adaptive thresh image. Keep forgetting to set that color map. CMap equals gray. Okay, so now we have our parking lot lines again here. So you can see that it did a pretty good job toward the left and toward the center. Off on the right, it starts to fail a little bit. Now, out of curiosity, let's go ahead and change this just to see what happens. So let's do the Gaussian instead. And you can see that it didn't fare nearly as well. So sharing that again. So that is just, again, showing you a different way of doing a sort of thresholding here. Now, you might be wondering, well, because I mentioned earlier on, I wanted to draw the lines using some sort of computer vision method. We are going to be doing something like this, but we are not going to be using specifically this. I just wanted to show you some more basic versions of how we could potentially do something. The thing about this, about thresholding like this, is it requires a very clean image, if you will. So even though my image here was very basic, like here, let's look at the raw image, or the raw image here. It's very basic. You can even see here like where the lighting got messed up a little bit. Like you could see a little bit more of a shading in the corner where the light source was more up in here, and then same over here. And nobody's gonna have a perfectly uniform image like this unless you have like a perfect lighting setup. And my whole thing is, so I don't know if most people are gonna get this. Understand, like, or maybe they've seen this before. So I like to go up to Naperville, which is a suburb of Chicago there, and there are these parking garages up there. And the nice thing about the parking garage is when you go inside the parking garage, there's a sign outside that says, oh, we have X number of spots available. And the way it knows that is because there's actually a sensor above every single spot that is pointed straight down, that it somehow knows, okay, there's a vehicle here, because there's even like a little light bulb there. And my whole thing is like, great, that works great, but how expensive was that to set up? And like, let's say even on the low end, let's say it costs $1 per parking spot. Well, if there's like 500 spots in there, a parking garage, then that's at least $500. I want to be able to show you that you can create this whole setup on a Raspberry Pi. So like this webcam here costs, I don't know, $50, and the Raspberry Pi costs $35. And have one of these and set up, and you basically toss it out and go, and then it basically emulates the same functionality of what these Naperville garages do, except way cheaper. And I said $500. That's way on the low end. Like there's all this whole infrastructure and piping set up, and if something goes wrong and the maintenance of that whole thing, I can imagine that thing, that whole parking detection system probably cost, I don't know, at least $10,000, at least. Whereas we can have a whole setup going with a simple webcam and a Raspberry Pi for less than $100. So that's kind of what my aim is here for. But again, my whole point here is, trying to use this basic thresholding here isn't going to work very well unless you have perfect uniform lighting, which is almost never going to be the case. We are going to be talking about I'm going to basically segment the parking lot lines from the background and actually detecting where the parking spots are at in a different upcoming live stream. But I want to just focus on image processing now with OpenCV in this particular stream. So, again, there's some stuff in my notebook here that I'm not going to cover today, so I'm actually just going to skip over this whole piece about morphological operators. Basically, what this is doing is different ways of processing the image in terms of, making it the foreground more blurry or less blurry, making the lines of the parking lot more or less blurry. It's just that we're already 45 minutes into the stream, and there's still quite a bit of content I want to cover. And just to be transparent, these morphological operators that I applied on these things here, as you can kind of see, didn't really have much of an effect. Like, it might have an effect on more different things. So I guess this one's kind of interesting, where I did apply this morphological gradient detection. But even then, because this was basically doing a very simple edge detection, even then, this is very similar to the same adaptive thresholding that we were just looking at. So I'm going to skip over this particular section that I did have planned, and I do want to cover color histograms. So let's move on to talking about histograms. So you all should know what a histogram is, I would imagine. So a histogram is essentially, it shows a distribution of values. So like I've already noted so far many times, we have 3 of these color channels for each of these images. And each of these images is represented by a different color value. So you may have, a color of red that is represented by the number 120, and it may be showing up a bunch of different times. And so the photographers and, a lot of different people like to look at the color histograms, because if you can balance out the histograms, then you can really change the contrast of the image. So let's go ahead and show you how to actually view the color histogram, and then we're going to show you how to actually level out the color histogram and then make a more contrasting image. So, and it's really going to make the colors pop quite a bit, and you'll see quite the difference here. So first things first, we have to set our color values. So let's go ahead and set a little tuple here that's going to represent our color values. So colors equals R G B. Okay, so red, blue, green here. And then I'm going to create a histogram here that is going to represent all 3 of these color channels. So we're going to, now this is, I don't know why CV2 doesn't allow, have a function that does all 3 of these at once. The function only allows you to process 1 color channel at a time. So that's why I'm creating this little tuple, and we're going to do a little bit of tuple unpacking. So because basically we're going to call this function 3 different times, once for each color channel, and then plot it on the same histogram all at once. So let's go ahead and iterate through our color channels here. So for I, color, so we're going to do the enumerate function in enumerate colors. Now, if you're not familiar with enumerate, because to be transparent, I wasn't super familiar with enumerate before, it's actually a pretty handy little function. Let me go ahead and just print out what it's printing. So I, and then print color. It's basically saying, okay, for this list of stuff here, give me the index value and give me the value itself. So I would represent the index value, so that is index value 0, and then the actual item itself, so that would be R. So 0 R, 1 G, 2 B. And the reason that we need this is because we need both of these different kinds of values for what we're going to do here. So the first thing that we need to do is we need to get the histogram values. And so the way that we do that is with hist values equals cv2.calcHist. And again, for some reason, you can only do 1 color channel at a time. We are going to be using our color image again here instead of working with our grayscale image. So we're going to pass in our image. We are going to pass in which color channel we need. And again, I don't know why we necessarily need to put the image in brackets, but just be aware that it is something that you have to do. So channels equals I eye. So we are going to be getting the color channel associated to which color that we wanted to do. So given that we're going to do all three, we're just going to pass in the eye variable here. Mask equals none. So what this mask parameter is basically doing is saying, okay, do you want to get the color histogram for just part of the image, or do you want it for the full thing? So if you want it for part of the image, then you would set the mask to be some sort of array of values that would represent whatever that part of the image is. We want to do it on the full thing, so that's why I'm setting it to equal to none. All right, so hist size equals, so obviously we want the full 256 color values. And then ranges, again, we want it to span from 0 to 256, so 0 to 256. Okay, so that's getting the hist values. Now we are going to do a plot of the values here. So plt dot plot is the hist values, and then we are going to pass in our color. So color equals color. So that's basically, so for this first one is going to be the red color channel. So it's going to get the red histogram channels, then we're going to plot it as a red line. Next one's going to be green and plot it as a green line, and so on. And then we are going to set an X limit just to be sure that, you know, that our X limit doesn't get crazy for whatever reason. So X limit equals 0 to 256. Now let's go ahead and show that. Okay, so this is the color histogram of our image, and this should not be surprising to you, as this is, you know, just showing again my parking lot here, my fake parking lot. I don't know why I keep pulling this up when I clearly have the function to do both, and I'm very proud of this stupid function that I built to do both. So, you know, this is my parking lot over here, and there isn't much to say in terms of color. Now, if we had let's say we took a picture of a landscape, like of a mountain scenery with a blue sky and a green forest, then we would see a wide distribution in this color range here. But so this should not be surprising to you here that we have a lot of these colors that are clustered right around the center here, because we basically only have essentially two colors here. We have the yellow and we have the gray background. Again, I have my stylized lighting on right now, so I apologize that things are a little bit wonky over here. But yeah, so that's what this is. So a lot of the stuff here is, you know, being spiked up here in the middle. Now, if we wanted to color equalize these things, so we could do so. And then what color equalization is basically doing is, imagine it actually works really well in this image. Imagine taking both of your hands on top of like the spike here and kind of pressing things down, and it kind of more generally distributes the color channels here. And what that is going to do is it's going to create a more high contrast image here. And so the way that we can do that here is first we're going to actually have to change the color channel of our image from RGB to HSV. So HSV, if you are not familiar with that, that stands for hue saturation value. And that is, we're getting into a little bit of territory where I'm not super familiar with what this is, but HSV basically is, like, I guess more representative of what the human eye sees. So I do know this. So I'm a little bit of an amateur graphic designer. I do print out things like wedding invites for people and stuff sometimes. If I have to print something out, I should have things saved out as HSV as opposed to RGB. And the reason is when I print the two things out, one of them clearly does look better than the other to the human eye. So we've been using RGB because RGB works great for computer screens. It's just for this particular purpose of doing the equalization of the color histogram, for some reason we do need this to be back in the RGB or the HSV format. So can you guess of how we're going to do this? So pretty simple. So HSV image equals cv2 dot cvt color. I'm going to pass in our image cv2 dot color, and then we're going to do RGB because we're in RGB, and then we're going to go down to HSV. All right. Now, I'm not going to do an IM show on it because it's going to look really weird to our human eye, because the Matplotlib renders HSV images kind of funkily. But again, doesn't really matter because we're going to convert this back into RGB anyway to show. But in order to actually run this equalization histogram function, it needs to be in HSV format. So the way that we actually run this function is we do HSV image So we're going to do : : 2. And so I think that what this is doing is basically applying this to the color channels function. This is I'm getting a little bit out of my depth here. I know this works because I've run this before. So CV2, but the way that we actually run this is, so there is a function called equalize hist. So we're going to go equalize hist. So we're going to pass in our HSV image again here, image here, and then same idea here. So HSV here. Okay. All right. So that looks fine. Now I'm going to convert the image, or I'm going to call this equalized image. Equalized image equals cv2.cbt color. Now we're going to take our HSV image and turn it back into RGB. So cv2 dot color, whatever. So we're in HSV to RGB. Is that right? I think so. Now, like I said, this is and we're going to show the histograms again too. This is going to produce a radically different image, but it's going to be kind of cool. And what we're going to see here. So plt.imshow, equalized image, tab autocomplete. All right, so now you can see a very highly contrasted image. So we're getting a little bit of the similar results that we got with our thresholding here. So we can more clearly see some of these light sources. So again, my lamp on the right, I guess I keep having this backwards. The lamp here is on the right, whereas my ring light here is on the left. Oh, I said that backwards. My lamp is on the left, my ring light's on the right. Okay, and then but you can see that the colors of the yellow really have popped now. So let's go ahead and look at the histogram here. And so this is basically going to be the same thing that we did before. So colors equals RGB, and then we're going to enumerate again them for colors for I, comma color in enumerate colors. All right, so now we're going to produce the hist values, and then equals cv2.hist, or calc hist, I'm sorry, calc hist. Okay, so this time we're passing in our equalized image. And then, so a lot of this is going to be like the same. I should have just copied and pasted it, but I feel like I'm cheating y'all if I copy paste stuff too much. So I equals channel equals I, mask equals none, hist size equals 256, and then ranges equals 0 to 256. Okay, then I'm gonna set the xlim plt.xlim 0 to 256. Now I do want to set a y limit here because I really want to drive a point home, because like by default Matplotlib is just going to look at whatever the max value is and set the y limit appropriately. I actually do want to grab whatever the y limit is here, so it looks like it's 160,000, just to really show you that this thing really did get squished down. So okay, so I'm going to run that, and channel. All right, what did I do wrong? Channels. Might help if I add that S. Might help if I actually plotted the thing too. All right, plt.plot hist values. Okay, so now you can see very clearly here. And by the way, if this looks funky, like why are there so many spikes here? This is actually common of the equalize function here, is that we got a lot of these weird little spikes here. But now you can see, comparing this, so we had this one giant spike here in the middle. It's almost like I was saying with the spike here in the middle, where we pressed it down and we equalized it all out. Now everything's kind of spread image here. So that is doing some equalization here, and you could even do if you wanted to alter the color channels even more, I think there's a way to do that. But I just wanted to show a more simple way of doing the equalization with the CV2 functionality here. All right, so that's all I wanted to show in terms of simple image processing. Of course, OpenCV offers a lot more things that we're not going to cover here. In this last part of the live stream, I want to cover what I think is the most fun piece, and that is drawing text and shapes onto the image. So the one thing I want to note here, because I'm going to be drawing the stuff on our equalized image here, so equalized image, just to show you this again. So these are arrays of values, numerical values. So whenever we write or whenever we do our shapes and our text onto these images, what it's basically doing is it's going to be changing these numerical values to represent what it should be appropriately. And basically that is going to be what I refer to as a destructive change. And so when I mean destructive change, I mean that like whenever we actually run this, whenever we run whatever, or like whenever we add a rectangle or we add a circle to the image, it's changing these numerical values to a point where there's no way to undo it necessarily. The only way to undo it is, having saved a copy of this variable elsewhere. So just be very careful. These are destructive changes to the images. So if you add a rectangle to an image and you're not happy about that, there's not really a way to change that. I mean, you could try to do it with some special blending and whatnot, but you're kind of screwed. So I guess the best thing you can do is to create a copy of your image. So I'm gonna create a copy here. So what am I gonna do? I'm gonna call this image eq. I'm gonna call this eq image copy equals equalized image dot copy. So if I screw things up, then I can just run this cell again. So let's go ahead and run our draw a rectangle onto our image. So let's just do a plt.imshow on the eq image copy. So just to show you again. So like let's say I wanted to draw a rectangle. So the way this works is pretty simple. It basically takes in 2 coordinate points that basically represents the top left of the rectangle and the bottom right of the rectangle. And so you can see here the x and y coordinate planes here. So like let's say I wanted to put a rectangle at this parking spot, basically covering this parking spot right here. So that looks like what? I don't know, x equals, or the top left corner is like what? X equals 550 by 500. And then the bottom right corner would be what? 750, or a little bit more than that, 775 by 800. So the way that we do this is simply by the rectangle. So cv2.rectangle. So the first parameter that we have to pass is the our image that we want to write on. So I'm going to do our copy. So again, because if I were to do it on the other image, these are destructive changes. I would have no way of undoing what I already did. So I'm going to pass that in. So the first thing that we want to do is pass in 0.1. So 0.1, now these are just basically the x and y coordinates. So I mentioned that if I want to cover this parking space right here, so what is that, 750, or a little bit more than 750, let's call it 760. 760 by 500. So that would be the y value. So x equals 760, y equals 500. So that's the top left corner. So that's 0.1. And then the 0.2 would be our next parameter. So 0.2 equals the bottom right corner. So that would be what? Let's call it 900. 900. I'm going to call it 900. And by uh-oh. Did my stream stop? Hold on. Sorry, I was just monitoring something on the right and something happened, and I don't know what happened. Okay, we're all good. Sorry. I hate when that happens because I always lose my train of thought. All right, so bottom right corner. So 900 by what? Let's call this 810. I don't know. That seems about right. All right, so that's basically what we need, and then we're gonna pass in a couple other parameters to represent the color and the thickness. So color equals, this is looking for the RGB format. So if I wanted to make this blue, so basically R would be 0, G would also be 0, and then we want to turn the blue all the way up, so that would be 255, and then we can add a thickness to it. So thickness equals 10. All right, so we went ahead and applied that. Now notice I did not save it back to in any sort of variable because again we are applying this directly on top of this. So this has already been applied. So if I were to go ahead and do a show on this, so plt.mshow eq image copy, then you can see we have this blue rectangle, and I was way off with my coordinates, but the point is made. That is how you draw a rectangle. So that's drawing rectangles. So next shape on the docket here, and the reason I'm showing you how to draw these shapes specifically is because this is what we're basically walking before we run. We are going to be using these exact same concepts that we are learning here in future live streams to actually do what we want to do to actually reach our end goal of creating this parking lot detector. So we're going to be working with rectangles. We're going to be working with circles, and then spoiler alert, I'm going to show you how to create a line here in a second. I know everybody. You're chomping at the bit. I know. Okay. So that's how you do a rectangle. So next one is a circle. So circle's fairly similar. So we're going to do cv2.circle. All right, and then we're going to pass in our image copy. So in this case, instead of passing in multiple points, we're going to pass in where we want the center of the circle to be. So let's say we want the center of the circle to be right about here. So what would that be? X coordinate would be somewhere, I don't know, let's call it 1300. And then let's call the y value, okay, so I was way off with what I thought here. What did I call this here? 500? Yeah, 500. I don't want it to be 500. I want it to be a little bit greater than 500. Yeah, like 525. Let's call it 525. All right, so that would be the center. And then you might be wondering, well, how do we know how big to make the circle? And the answer is by setting the radius. So we will set the radius to be however many pixels we want. So I'm going to call a radius equals 100. Now these next two parameters are going to look similar to you, but I am going to add a little bit of a twist on this next one. So let's make this a green circle. So the way that we do that is turn off red, turn green all the way up. So RGB 0, 255, 0. And then thickness. So thickness equals. Now, let's say you actually did not want an outlined circle, but you wanted a filled-in circle, or even a filled-in rectangle for that matter. If you wanted that, the answer is -1. So let's go ahead and run that cell, and let's go ahead and display this again. plt.imshow. What am I showing? Eq image copy. And now you can see that we made a green circle right here. So now you can see how we did the circle. Now, last shape before we add some text, I want to show you how to create a line. So let's draw a line from the top corner of this parking lot all the way to like over here, like right there. So this is going to look pretty similar to you again. It's just as simple as running a little function from CV2 here called CV2 line. I'm going to take a quick sip of my drink. Okay, CV2 line, eq image copy, point. So this is basically just going to take 2 points, one representing the one end of the line. So it's technically a line segment for you math people out there, not a line. It's a line segment. So this is the first point of the line is going to be what? What is this? I'm going to call this 200 by 200, 200. 200, and then 0.2. All right, then 0.2. PT2. Oh my gosh, can I type today? 0.2, and then I wanted to put it right over here. So what was that? I'm going to call that 1700 by what? I did a little bit better with my green circle there. So what was that? 525. Yeah, 525. 525, and then we can add. Let's make this a purple color now. Where's my preschooler and kindergartner at? How do we get purple, people? And it is as simple as turning up 2 of the color channels all the way. So how do you get purple? Red and blue. So red's gonna be 255. We don't want any green, and we want all the blue. And then let's add a thickness. Thickness equals. Let's make it a thick line. Thickness equals 15. All right. So we've run that. Now let's do it. plt.imshow, eq image copy. All right, so now we created this thick line. I did pretty good on nailing where the coordinates at. I mean, this could be over just a hair more, but not bad in general. So that's how you draw some basic shapes. And again, we will be using these shapes intentionally, and you will see how I will be using these shapes. And there actually is a way to start a video, and with your mouse you can actually click like, okay, I want, like, let's say I was drawing a line, I want this point to be here and this point to be here. You could do that, and I've actually considered incorporating that as part of this project. However, maybe not. I don't know. I haven't decided quite yet. Anyway, so that's how you draw some basic shapes. Now let's show one final thing, and that is how to do text. Now, the only thing that I'm personally disappointed with when it comes to text is that you can't use custom text. You are limited to whatever fonts that CV2 has it after. So I'll go ahead and set a preset of font variable. So font equals CV2 dot font. So, and then if you do a tab out complete, you can see these are the different kinds of fonts that we can use. I personally just stick with the simplex here because this is a very basic, I don't, not Helvetica, but like almost Helvetica looking font. So that is setting the font. So unfortunately, those are the only fonts that we can choose from. And then so this is as you can guess, like this is going to look fairly similar to what we've already done so far. So cv2.put text. All right, so we're going to pass in our equalized image again. All right, so we're going to put text equals, I'm going to say, I don't know, hello streamers. I'm going to call it hello streamers because you all are my people. I don't know what that means. All right, so now this is where basically where you want the text to be at on the screen. So where we, if you recall, the rectangle 0.1 was the top left corner and 0.2 was the bottom right corner. Org represents the bottom left corner of like where your text would be. So like, let's say I want my text to be in this region right here. Then the bottom left corner would be what? Not 100, 200, and then what? 1,000? Yeah, let's call it 1,000. Let's call it 1,000 just to be safe. So 200,000, and then we can set a couple more variables. So font face equals font. So this is the same font that we just established earlier, and then we can set the size of our font. So just note that with this font scale value, just note that the font gets really big really fast. So you don't want like your inclination may be like, well, I in a Word document I typically write things at 12-point font. Don't do that here. Don't like start small. In fact, I'm going to keep it at 5. Let's set a color. Let's make it red text. So color equals, turn up the red channel all the way. 25500, and then let's make the thickness 10. Thickness equals 10. All right, and then let's go ahead and view this guy. plt.imshow. Image copy. Okay, hello streamers, and that brings us pretty much to the end of the stream. I guess there is one more thing I want to say. So that is how you add the text and the shapes and stuff. And this is all stuff that we are going to be applying in future streams. But that's basically all that we want to do. Now, let's say, we're happy with this thing here that we've created and we want to save it out for whatever reason. Let's go ahead and save this out using a special function. Now, just as we read in this the original image with the CV2, and it was a BGR format. Just note that whenever we save it back out, we also have to have it in the BGR format, or else it's going to look really weird. So we're going to save this out. So I'm going to call this image equal, or final image equals cv2.cbt color. So this is in the BGR format or RGB format. So I'm going to call it image copy. cv2.color RGB to BGR. Okay, and then finally the way that we actually write this thing out here, let me just yeah, that's right. All right, how we actually write this thing out is cv2.imWrite, so image write, and then we give it the file path that we want. I'm just going to keep it in this current file path, so I'm going to call it post processed parking lot.jpg, and then I'm going to pass in the final image. All right, and then so it returns this Boolean value. Now, if I were to come back in here into my notebooks here, so this is where I'm running this notebook at. So this is the image that we have been working on. So that is saved out as a JPEG file right now. And so that really brings us to the end of today's live stream, and which is good because I can feel my voice going. I hope you learned a lot here. And again, this is not like a robust covering of OpenCV. You can do a lot more image processing with OpenCV, but I want to give a primer of what to expect as we continue to proceed forward with this project, because we are going to be using some of the same things that we've done in terms of writing the shapes and whatnot, but we are going to be doing some additional things of how to actually segment the parking lot lines from like the background here, in an automated way, in a way that I'm doing things with the camera and nothing else. So I'm looking forward to that. I hope you all enjoyed this stream. I'm hoping to do one more next week. I would like to do another stream next week. Definitely won't have one in 2 weeks. So in not this coming Sunday, but next Sunday, I'm taking my family to Disney World, and I will just be flying back because I usually do these streams on a Friday. Today's Saturday, just because yesterday was Black Friday and I was still full from eating turkey and stuff the night before. But yeah, maybe we'll do another live stream next Friday, and we'll see how things go. So hope you all enjoyed this one. Thank you all for joining. Hope you all have a great weekend, and we'll close it out there. I'm at a loss for words. All right. See you later.